particular lecture is probably going to be pretty similar to the other one, just because the problems I have picked out, I can't really deviate. So just if you're watching this one to get a different perspective, it's probably exactly the same or very close to the same. That said, I want to start with the problem here, 2.6 in the workbook. I'll screen share. 2.6. And I'm going to start with this one. And what I'm going to try to do is get you used to dealing with the letters again and word problems, because I know we did some graphing. If time permits, at the end of class, we'll do another problem with graphing, okay? This worked out last time, okay. So I'm going to write this up. Now, if you might already have the solutions open, but if not, maybe you should try writing up what you think this should look like. Notice I didn't give you a picture. So this is one of those ones where the solution has the picture. And I'm hoping that you might try and draw your own picture, and then we can discuss. So I'm going to do the same thing. Maybe don't look at my whiteboard for a minute. Okay. So I started drawing this one. And remember, at any time you can chat with Memo anytime you want. All right. And Memo, remind me afterwards, I was going to tell you something about that we might try next time. Let's talk after for just a minute, okay, Memo, at the end. All right, so this is what I read. I said there's a total distance d, there's some time to react. So what I did is I naturally split this into different chunks. And so I'm going to do two different one-dimensional motion problems. So I'm going to list out my knowns, x1, v1 initial in the x, v1 final in the x, etc. And then I'll do it over here. So I've got two different scenarios here. And so I call this a multi-stage problem. There's stage one, or the reaction phase, and then there's stage two, the braking phase. So I split it into a react and a brake stage. And then it's easiest just to call them stage one and stage two. And so I'll try and remember this all day today as we're doing a couple of these. I'm going to try and use blue for stage one and red for stage two, but if I screw up, you can let me know, all right? Colors don't really matter. What does matter is this. What are we trying to do? We're trying to solve physics problems with a minimum amount of pain, all right? And so the idea is we want to clearly organize our work. Notice I've not only changed the colors, I've changed the subscripts, and I've also changed their locations on the page. All I'm trying to do is find a way to be organized. This problem, you could try to do it in your head, and I think you would start to get lost. Whereas if we're very well organized, usually the solution to the problem will at least slightly present itself, or you'll know where to start looking for a solution. Students that just do whatever they want and scribble all over the page, sometimes that works really well. The easier the problems are, the more often that works. But in reality, as problems get harder and harder, organization is key. That said, let's go through this and see, in this case, what out of this we can figure out. All right, so help me out here. Do I know what delta x1 is?
0.
No. So I'm not sure. Okay, so let's make sure. Delta x1 would be the time it takes to get from here to here where I apply the brake. So this is supposed to be the instant that I'm applying the brake. So do you think that that displacement would be 0? Probably not.
No, so we don't know that.
Yeah, we don't know it. And that's good. Do you agree it's not the total distance? It's not D. That's what I was looking for. It's not
Right.
D. Yeah, good. All right, so somebody else. Do I know V1 initial X? And this would be the initial velocity of the object in the X direction at the beginning of stage 1.
It's constant B.
V. And that is known because that was given in the problem, right? Nice. How about at the end of stage 1?
Still V.
It's still V. And so I'm going to draw that in here. At the end of stage 1, how do you know that it's still V?
Because that's when you're starting to react, so you haven't pushed the brake just yet.
Exactly. And the problem also said constant speed over that time, right? Good. So what's A1?
0? Because it's constant.
0. If you have constant speed in a straight line, your acceleration is 0. If you have constant speed in a circle, we'll learn in next class that's not true. Whatever. Okay, time. Do I know the time for stage 1?
We don't know it.
We do. That
we
was
put it-
TR. And so so TR, it looks like we don't know it, but we were told TR in the problem. So that you have to assume is a known. Does that make sense? Because it was one of the words given or one of the symbols told to us in the problem, we're supposed to assume, aha, that's a known. Is that okay?
Yeah.
Yeah, tricky, right? Okay, let's go over here. Do we know x2? That's this distance. I should be careful. This displacement.
No.
No. Why is it okay for me to use the words distance and displacement interchangeably on this problem?
You're only going one
Okay.
way.
Yeah, it never reverses direction. So on this problem, I'm going to be sloppy and keep switching distance and displacement, but that's only because it's not reversing direction. In general, this should always be thought of as horizontal displacement. Okay, what's V2 initial? What's the initial velocity in the X direction at the start of stage 2? Go ahead.
Constant velocity.
Yeah, that V. And then a second later, the brake is hit and you're going to be slowing down, right? Or this is right as the brake is being hit. Okay, what's the final velocity?
0, hopefully.
How do you know?
Uh,
What were the key words?
Before hitting the deer.
You
so
stop
0.
before hitting the deer. Excellent. Do I know A2X?
No.
Negative.
No. Yeah, we do think it should be some negative number. So in the solutions, I actually said negative A, where this is the magnitude. Or you could just call it A2X for right now. But we don't know what it is. We expect it should be a negative number, and it's going to have some magnitude A. Good, good. Do I know time 2?
T minus TR?
Do I know T? Do I know the
No.
total time? Nope. But that begs the question, there is another thing that we know here. 2 of these terms are related. Which 2? And what is the relationship? Two of these things are related to each other, and what is the relationship in equation form or word form or any? Maybe that question doesn't make sense.
Yeah, I'm not exactly understanding what you're saying.
Okay, so let me put it this way. One of the terms over on the blue side is related to one of the terms on the red side by something up in the picture. So one of these things and one of these things over here are related to something up here.
Is it the constant speed?
Well, you're right. That's true. But I'm thinking it's something with the question mark. So how?
So is it the x1 plus x2 equals d?
That's what I'm looking for. So that's called a constraint. What we have here are two totally different problems, but we do know that the two distances, and strictly speaking, in this case, we could say distance or displacement, the two displacements should add up to the total displacement. Since they're only going in one direction, we could say this. Right? And so this is another thing that we know that connects these. This is how these two-stage problems tend to be different than the single problems. For example, in all these other problems, we'd come in here and there'd be two question marks and we'd just be like, okay, got it. What we have to do now is we see that there are actually on average two question marks per problem, but we have to use this problem to figure out one of these so that we could do the rest of that problem. And that's the next level. And this is why if you're just organized, you're like, well, shit, this isn't too bad. Okay, I'll write out my equations for this. I'll write out my equations for that, plug in the zeros, see what drops out. And that should help me as long as I know this piece of information as well. So if I reorganize this one, I'm just going to show you that this is equal to d minus delta x1 in this case. Does everybody buy into that? So all I did was I rearranged this to solve it for x2. And so what we see now is, even though this is unknown, I see if I could figure out this thing, I would, in theory, know that thing, which would then, in theory, help me figure out these things if I needed it. And that's the strategy. Oh, go ahead.
I was gonna say it's like a parameter, right? And then also too, I noticed that that's one of the things that got me super confused on the lunar landing one.
Yes, yes.
Yeah, I was like, oh my god, like you only have two knowns, and I was like, how do you solve this? And you used, I think you called it a constraint. Yeah.
A relationship between two different problems. Yeah.
And it's kind of like a system of equations kind of thing, right? Like
exactly. And that's what we're doing. So we could count these up. We have 1, 2, 3, 4 things we don't know. And so if I want to solve for that, I need 4 equations, independent equations, right? So we need 4 different equations to solve for 4 unknowns. And so this is going to be one of them. And then we could use kinematics equations, 2 kinematics equations from the red side and 1 from the blue side. And then we've got 4 equations, and this will have a solvable system of equations. Yeah. What do you think? Should we go ahead and write some equations and see where to go from here? Let's take a look. So on this side, from experience, I happen to know the only equation that matters for this side is going to be this one. Where this equation, it's the delta x equation. If I plug in that ax equals 0, this rapidly becomes very easy. Look at this. This is just distance equals rate times time. Excuse me. In this case, remember, you may have remembered me telling you that delta x equation is distance equals rate times time on steroids. Well, here, all that extra term was, okay, what if the rate is not constant? That's the next correction to distance equals rate times time. But so, all right, here we go. And again, in this problem, distance and displacement are interchangeable. So it's okay to do that. So that's V times TR. This was a known, this was a known. Now this is known because we know both of those things. All right, so that means I know this. So that means I know that, right? I know this sounds crazy, but look, this, whoops, let me use a green. I haven't used much green here. This is a given. This is a given. We know both of these numbers in theory. If I know both of these, that means in theory, I should know that one. Well, now I should know this one. I know that one. That means in theory, I should be able to figure out that one. So now this one, tentatively speaking, is no longer unknown. Yeah, we've got to do some work here. We got to plug this into there, but for the most part, we've got it. So now I'm going to write the red equation here. I know in this case, what do we have here? I know that V to final X, I'm going to do the squared equations. And that's got a little bit of glare. We'll kick it that way. So in this case, I know this is 0. And so I'll get 0 is equal to V squared plus 2 times negative A times this junk up here. And at some point, I've got to go to the solutions here to show you what this works out to be. Oh, excuse me. Woo. Sorry about that. Didn't have time to. Yeah, thank you. Didn't have time to hit the mute button there. All right, let's go take a look at this solution here. What was this, 2.6? There we go. So this is kind of pretty similar to what we were just working through. Let me get out my annotation here. Here is the constraint or the connection between the two. All right. And notice this one's going to be, notice again, read all these words carefully. So the rate of slowing is going to be this A, and the direction is the minus sign. All right. So that's why I plugged in a negative A right there. That's where that minus sign comes from, right there. We kind of already explained this one. I think that one's not too bad. And so if I could go down here a little bit. It looks like I gave you the magnitude. And then, so there's some algebra there. That's not very exciting, but I'm sure you could do that and you should do that. So what did I do? I checked the units. And then notice this, I did a reality check. So suppose you're, you know, 1/10 of a mile from the deer and you're going 60. Can you do this without dying? Let's find out. And so blah, blah, blah. And so I said, okay, if that's the case, I got 2/3 of a G, right? And I saw that performance vehicles can brake at about 1 G. So this probably seems okay. Maybe a Buick could do that almost. Probably not a Buick. Buicks are pretty heavy, but yeah. So this isn't outrageous. Oh, go ahead. Sorry about that. What'd you say?
Oh, sorry. I was making a comment about the Buick.
Oh, yeah. Did you have a Buick?
No, I was just saying they're boats.
Mm-hmm. Mm-hmm. Yeah, I used to have a Buick. I tell you what, it ran pretty well, but man, it would go through brakes like crazy. I would take it up in the mountains, and Buicks just chewed up the brakes. So yeah, anyways. But yeah, so, and notice the kinds of things that the checks bring up. I know this maybe seems like a tangent. I do want to point this out. If you do the problems algebraically, it allows you to talk about real life in different scenarios down here, and you could compare different vehicles or things like that. And so maybe this particular problem is very contrived and very silly. Yes, but we do see that there's a merit to doing things algebraically. It allows us to check different kinds of things and only have to do the problem once. So, all right, that's pretty good on that. So let me pause for a second. Are there any questions about this kind of procedure here? The big picture again is, okay, we've got a complicated problem. I'm going to split it up. I'm going to organize my work in some way and keep track of the 1 stage and the 2 stage. I know the final from stage 1 is equal to the initial from stage 2 for velocity, right? Your ending speed for this one, or your ending velocity for this one, should be your beginning velocity for the next stage. And so from there, you're kind of off to the races. All right. Speaking of races, let's go look at question 2.36 in the workbook. I'll share screen. There we go. Page 41, it looks like. So this is another one where I didn't draw the picture. So this is a good one. So you could try and draw your own picture and I'll draw mine. Try not to look at the solution at first. And let's focus just on getting part A. Okay. So we're just going to do 2.36 through part A, and then we'll go beyond that in a minute. So we've got a snail. We got a cop. And just for this problem, I'm going to drop all the X subscripts, okay? I'm going to just assume everything has an X on it, and you can do that too, just to reduce clutter. In chapter 4, we wouldn't want to do that, so that's the next chapter. But for now, you don't have to write the X all the time. I think you've earned it at this point. And I'm using 1 for the snail and 2 for the cop, if you guys want to match up to me, okay? 1 for the snail and 2 for the cop. All right, I've got all my stuff written, I think. Yep, okay. So this is how I interpreted the picture. You got the snail. All right. So the snail is here, or the speeder is here, however you want to think about it. Here's the cop. Man, would you look at that S car go? Ouch. Everybody loves a good snail joke. All right. So, anyways, it's just Zoom. Yeah, it must be Zoom. That's why you're not laughing. Yeah, that's it. That's it. Okay. So, yeah, here we go. I'm going to split this problem up into 2 stages, and then we are asked to find the maximum distance between in part A, right? So in this case, I'll write down my speeder here. Oops, ones. I don't know this. This is V, this is V, this is 0. I don't know that. Not looking too good. I'm going to come over to here. All right. It's a little sloppy, but here I know that this is A. I know that this is 0. I don't know this. This is not looking good. I don't know this. Do we know V2 final? Is that given to us?
I don't think so.
It is. In a weird way.
Eventually, they're gonna reach the snail, right? So that'll be V.
Careful. If they reach the snail, is the speed going to be V, or is it going to be bigger than V, or is it going to be smaller? If you catch up to somebody, are you going their speed, or are you going faster than them?
Faster.
You'd have to go faster, right? So, yeah. So now we do know this. The words maximum distance between tells us V2 final equals V. Now think about this. If you were going slower than V, this person, the snail, will get farther and farther ahead of you. If you were going faster than V, you'd be catching up to the snail. If you're going exactly the same speed as the snail, that happens to be the moment when you change from losing ground to gaining ground. That would be the instant when you have maximum separation. So what are you supposed to know as a physics student? This is called an intercept problem. The cop is trying to intercept the speeder. We know that the maximum distance between, those are key words in a word problem that says, do that. And once you do that, and so somebody said V2 final equals V, and that was correct, but I think you said for the wrong reason. It's not because they catch up when you're at this speed. That's when you start gaining on them, would probably be a better way to say that. Did that make sense? Hopefully.
So when your speed equals V, that's when the distance between them starts getting smaller. That's what
That's
you're
correct.
saying?
Exactly. So at the exact instant your speed is V, you're neither gaining nor losing ground. Think, if you were driving exactly the same speed, if you're driving 70 on the freeway and somebody else is driving 70, your cars stay equidistant, right? But if you're going more than 70, you're going to catch up to them. If you're going less than 70, they're getting ahead of you. So it's that kind of thing. Esteban, you good?
I still don't understand how the final velocity is equal to V.
Be careful. We're not worried about them catching the person. It's the problem statement said, what is the maximum distance between? The
okay.
The final
Okay.
velocity when you catch them is very different.
Okay. Now it makes sense.
Okay. Yeah. All right. In fact, go ahead.
So wouldn't the maximum distance be higher while they're accelerating up to V? Or does that make
No,
sense?
no, because they start out together.
Oh.
And so, right, at first, the distance is getting bigger and bigger and bigger, and it keeps getting bigger until this person hits the same speed, and then they start closing the gap. Here,
Okay.
I got something for you. Memo, you lucked out. You're in the second section. I had the student in the earlier section make this code for me. And then I modified it. So you got lucky, Memo.
Yeah.
All right. So let's take a look here. Give it a second. Okay. Hopefully this is up on your screen right now. Did I color code this right? I think I did. So this is the cop. And down here is that escargot. And notice the speeder has this speed V. Now the green arrow is supposed to be velocity there, okay? So the green arrow. Notice the cop has no velocity, but they are going to accelerate. So if I click on this, we're going to run this, and I just pick some random numbers. Right at that time, now the cop is catching up and closing the gap. And so notice the speed of the cop at the end is actually greater than this speeder, than the snail. But we see, let's just run this one more time. I have no idea how this is running over your... And so it looks like, I'm just going to kind of guess. Looks like maybe right around in here somewhere. I could be wrong, but somewhere in that region seems to be where the cop starts gaining. So let's try running this again. Look at the velocity arrow. Same size, now it's gaining. So it was a little earlier than that. All right, and so let me clear these. Hold on a sec. Okay, and so what I did down here, if you scroll down, this shows you the position versus time graph. And boy, it sure makes this easier to see. Somewhere right around in here, yeah, right about here, you can see the distance between them is largest. So if I could, right here, that looks like the time when I have the largest distance. So at about 4 seconds. This one over here is at about 9 meters. And this one over here is at about, this is kind of goofy axes. It goes by threes, but whatever. So what is that? Maybe 4 or something? I don't know. But yeah, so I can't, it's kind of a screwed up axis. 3, 5, 8, 10. So it looks like it's going by 2.5s, but it's rounding them. Do you see that? I think it's going by 2.5s. So I think this is actually 2.5, but yeah, okay, whatever. That's yeah, who cares? We get the idea here. Now, if you really want to get spicy, what we could do, you could go into here and run the simulation. We could do this later. Instead of, so this is going for the entire distance. So you could say, I'm going to change this to velocity. Whoops. Oh. And hopefully I don't screw this up. And so we'll run this one again. Hopefully I didn't screw up my typing there. And so that is the time when this transitions. Notice the 2 velocity arrows are equal. After this point in time, the cop is going to catch up. And so I don't forget, I'm going to go back in there. So all I did, that's, you can see how computers would definitely make this a nice thing, right? So eventually, what was this? Pause.x. So that's, if you set their positions equal, and there's a less than or equal here for reasons I don't want to go into. But if you set their positions equal, that's when they catch up. That's part B. So when we run it until they meet each other, that's part B of the question. And after this, I'm going to go back. And obviously I just picked some random numbers here, but if you want, you've got this. And I think I sent this in an email to you, but I could send you another version. I added the arrows after she did this. So this gives you all the different stuff. You can catch the time, you can get the speed, etc. All right. So what was I doing? What did I want to do? Oh, I wanted to show you the question again. And this is one of the goals of, geez, right here. So you as a physics student are supposed to learn from this the following. So write this down somewhere. They have the max separation when the velocities are equal. And then a lot of you said, how far will they catch up? Overtakes. That's what says they have the same delta x. And so you're supposed to know that just in case this type of stuff shows up sometime. Any questions about that physical principle that we're saying? The maximum distance means velocities are equal. Overtaking them means the x's are equal, so to speak. Hopefully that makes some sense why we're doing that now. Okay. And you could always ask Memo if you want as well. So now I'm going to go back in here. I'm going to write some equations down, right? Well, when A equals 0, there's only one useful equation. It's delta x1 is going to equal V. Oh, maybe you notice this. Do you agree that in this particular problem, the speeder and the cop are driving for the same amount of time? Does that make sense?
Yes, for when the cop catches the speeder.
Yeah, so this is different than the last problem. In the last problem, there were two different times. I'm going to erase this time subscript because that's just one. In this special case, they do have the same amount of time. The cop starts the instant the speeder passes. So this one would be just VT. And that just saves me writing a subscript right there. Okay. Now over here, let's see, V initial, I think I'm running out of room. Well, we do know this, right? So what we could do is, I'm running out of room. I need some space. So I'm going to get rid of this. And I'm going to put this up here. Girls! Sorry, my kids are going crazy. Hold on a sec. Girls, doors are not toys. You want to get me angry? Ah, the joys of children. All right. That's how it goes. That's how it goes. All right. So in this case, now we have this one has no initial velocity, so that term's going to drop out. And then we're also going to get, oh, I should just do the extra steps. Right. And so in this case, this is 0 and this is 0. And so from there, we get, I believe it's pretty easy to get the time here. Once I know the time, I could plug that into this equation. I could also plug that into that equation. And then, does anybody remember what we're trying to find in this problem?
The maximum distance between.
Yeah, so what would that be? Yeah, doors are not toys. Yep. I keep telling them that. I just don't want them to lose a finger, you know. Anyways, Yeah, so in this problem here, we're trying to find the distance between. So is that x1 or x2? What do you think?
It would be wouldn't it be x2 minus x1?
Nice. Actually, which one should be bigger in this case?
Well, okay, x1 would be bigger because the snail's ahead. So x1
Yep.
minus x2.
Nice. There we go. Right on. And so that's yeah, you could do that. It'd be interesting. Actually, what you could do is if you really wanted to, like in that simulation where we had the plots, you could actually set the code up to plot the distance between versus time, right? And that would be, where is that? Right. So if you could plot this one and that one, couldn't you just subtract them and plot it? And in fact, I bet we could. Let's see, where's that plot? We could just do this. And then I'll comment this one out. So when we run this thing, oh, I think I did it backwards. You see that? Whatever. All right. So I did the wrong subtraction because their 1 and 2 might not be the same as our 1 and 2, but you get the idea there. I'm going to change that back before I forget and be done with this simulation. But yeah, so that's what happens if you pick the wrong one first. Where was that? So yeah, this 1 and 2 might be backwards from our 1 and 2. All right, so we're good to go. Making sure this runs again. Looks good. All right, enough of that. All right, so how are you feeling on this? Okay, medium? Is this bad? I'm going to sit down for a sec.
How complicated are the equations on the test?
They're
So I feel like
easier than these.
I feel like I do really well with like the
Simple.
kick the box up the ramp and all those, you know. But once it comes to like the lunar landing, I'm just like
Yeah, great question. So I would say this. These questions that we're doing today are harder than the ones that are going to be on your quiz. That said, these are easier than the ones you get in 161 on a test. And so like the ones on 161 in a test, it's like getting punched in the face 10 times. But so what I would say is I still think these are worth practicing, even if you struggle with them, because I think you realize how much easier those other ones are and get better at them. It's for me, it's a lot like weightlifting or something. If I was going to lift weights and I needed to push a 50-pound box all day, I would want to train pushing 60 or 70. That way, when it gets time to work, I could actually do it all day. So you're kind of overtraining a little bit. I don't know if that analogy made any sense at all, but
yeah, I understand what you're saying because I've heard that about you, how you're really hard, but you're much more prepared for the next class.
that's what I'm,
Versus,
yeah, exactly. And I don't know, I debate whether that's a good idea or not, right? Because if you're really hard, you might not pass everybody. But the ones that do pass are going to be better prepared and then are more likely to succeed when school costs 10 times as much. So I don't know. I'd rather have you guys kind of hate me and have to deal with me here. But then when you transfer, you don't have to, think that you're not good. So if you could make it through my class, you're certainly good enough and you deserve to transfer and all that stuff. And yeah. And some of you that maybe get D's, it's questionable whether, oh, could I have been a little nicer to you? Maybe, but I'm trying to prepare people for sure. Sorry if I went on there. Esteban, is that good on your comment?
yes.
Your question? Yeah. So when you're working on these problems, work on them. If you get stuck and have to use the solution, don't feel bad if you have to use the solution on the 2-stage problems. Okay. Just learn from them. And then next year, when you have to take me for 161, it'll be easier because that class just, It gets intense. Yeah,
Yeah, I'll
Memo.
be there in the fall.
Exactly. Oh, spring or wait, are we fall?
All right, sorry, spring.
Yeah. I got you.
I don't know where I'm at right now.
Dude, I know what you mean, man. It's crazy. Time just is weird right now. Memo, do you have any thoughts? You want to unmute and give them any thoughts on these? What worked for you or not?
On the problems?
On just on 1D motion and what worked for you or any advice you have. I don't know if you can remember back that far when you were in 110 or whatever, but or did you
Yep.
even take 110?
I took 110 with Tobin.
Hmm.
I took
gotcha.
161 with you.
Right.
But I think going like just doing the problems over and over again is that's what helped me. Just do it, over and over again. Side by side with the solutions sometimes would help.
Mm-hmm.
Just to get me just to think a little bit different. And some of these problems require you just to think a little bit more and differently than you would. So you just got to read everything into account and just take everything.
Careful reading is probably pretty important, wouldn't you say, Memo?
Yeah.
It's like, is that usually most of when you got stuck on these? What were the kinds of things? How did you get stuck?
How did I get stuck?
Yeah, when you were was it usually because you didn't read something carefully, or was it just random algebra, or what? I mean, the algebra probably you were great at, right?
Yeah, the algebra is okay. It's just thinking how to say it. It was just because with these problems, it was just.
I mean, you were pretty good at these problems too, right? So you maybe didn't have a ton of problems with them, but I don't know.
No, but I would just draw out a list of the knowns and unknowns and then just question myself. Well, if I have this, if I know this in the question, do I know this? Like if it says max speed, do I know, okay. Do I know that, I don't know, whatever.
I got you. So relating the words in the word problems to the things in the list. And that's the tricky part, I guess, right? Is making sure you understand the secret knowns from the wording of the problem. When things say at rest, you're like, oh, something's zero, right? Some velocity zero. Right on. Or like max separation. Oh, that means set these two things equal. Oh, catch up. That means these two things are equal. So once you get, and I think we've seen all the weird cases that might show up now.
Yeah.
All right. So that said, that's it for this chapter. We could do another problem. Yeah, what do you think? You guys, what do you guys need most help on? Is it word problems or graphs, or do you want me to try and find one that does both? What do you think? Word problem?
Me personally, I feel kind of comfortable with the graphs. And so the
Okay.
word problems is I guess my problem is visualizing the problem, and so sometimes it's hard for me to decipher what the paragraph is trying to say.
Mm-hmm.
So right there where it's just in this, for instance, in this question we just did, where it says what maximum distance between the cop and the speeder, I couldn't really understand what that. Now I do. Now that you explained it, I'm like, okay, that makes sense. But at first, if I were just right off the bat, I couldn't understand what that meant.
I gotcha. And then let me see. I'm reading Jacob's here. Yeah, drawing the picture, figuring out the knowns and unknowns, and then getting to what equations. So so let's try. Visualizing these is no joke, right? And so why don't we try the Lunar Lander one? Is that because you said you got lost on the Lunar Lander? It's not the same problem that I did earlier, but it's got XTV, or it's a vertical problem, and I think this would be a good problem to do because it forces us to visualize it. Plus, it addresses one of Esteban's questions from earlier, right, Esteban?
I think it was the Lunar Lander one.
2.23.
I can't remember which one's the one that had that.
Yeah, let's try it. I'm going to try it. So everybody, let's try 2.23. And this will be slightly different. So if you need a different problem worked, I actually did 2.22 in the earlier class in the last 20 minutes or so. So let's take a look at 2.23. I'm going to bring it up. There it is. I was trying to imagine with this problem how difficult it must be to land on the moon. I just can't even imagine. Can you imagine being the astronauts trying to land on the moon? That must have been just horrifying. I guess that would, and yet it'd be thrilling, but geez, you're just like, dude, the odds of you making it back alive are so low.
That was-
Anyways,
And that was back when, you know, my phone has more capability than their computer at that time.
oh yeah, oh yeah.
They didn't have no computing power.
It's crazy. I mean, obviously they put in enough to, but I guess in some sense you could see this part of the problem is fairly basic. But yeah, let's take a look at this problem and just try to get an appreciation for just one phase of that massive trip to the moon. All right. So okay, we have this one: a lunar lander free space can use its thrusters. Oh, that probably shouldn't have a apostrophe there. Whatever, that's fine. Sorry about that. Okay, so the free fall acceleration is g/6 magnitude. The lander is 200 meters above the moon. Let's say it's moving downwards with this speed. The lander falls freely until it reaches this height above the surface. From height until the ground, the thrusters are fired at max rate. So basically you're falling, and then you get close to the moon. When you're distance h above the moon, you fire the thrusters and try not to die. The speed of the lander is approximately 0 just before impact. We're going to ignore the mass of the fuel burned, which is not true in real life, but hopefully it's approximately true. And so this would give you an idea approximately where you need to fire. All right. Oh, I don't even know. Yeah, I don't know what that is. So I'm just, yeah. All right. So I'm going to go ahead and draw the picture, and you could draw what you think, and I'll draw what I think. And then I've got it in the solutions, but try not to look at it at first. You know what this reminds me of is the deer in the headlights, right? So you have something that's moving with constant speed, and then you're going to accelerate. It's exactly the same problem as the deer, only now it's going downwards. So we're going to maybe have some minus signs we got to deal with. Same exact problem, right? In terms of the algebra. Okay. Whoops. So we got this scenario right here. Okay. So in this case, this thing's moving down with some speed. When you're distance h above the ground, you're going to fire the thrusters. And what did it say? V final is approximately 0. Oh, this is not exactly the same as the deer in the headlights. This is trickier a little bit. Think about this. Is this one going to be going at the same speed? Right here. So this, it's starting out, it's moving at 20 meters per second straight down. I think that's what the problem said, right? Yes. And now, what's the speed here? Is it 20? Is it bigger? Is it smaller?
It's smaller. No, bigger.
Yeah, we'd expect as you fall down, shouldn't you speed up? And so now look, is this speeding up? Do acceleration and velocity point the same way? They do, speeding up. They're both negative. All right, so we're expecting some number here. We'll say V2 initial. I don't know what it is, but I do know it would be the same thing as V1 final, right? So in this case, the connection between the two problems is that they're two velocities. The ending of stage one is the beginning of stage two. So this is a lot like the two x's add together to get the total distance. There's some weird equation that connects the two. This is the connection in this case. All right. And so while here, I'm going to leave off the y's or I'm never going to get done here. So there's some equations that I have here. And in this case, the velocities are all non-zero. I do know what is AY in this particular problem.
G6.
Nope.
Negative G over 6.
Negative G over 6. Now, if Esteban had flipped his coordinate system over, he's right. But Esteban, did you flip your coordinates or not? You may have, I don't know.
No, I wasn't thinking of the negative.
Yeah, so this is a cool reason. Like when you look at this problem, this is the case where wouldn't it make sense to call down the positive direction? Think about this, y. If I called this way positive y, then this would be positive, delta y would be positive, everything would be positive. But since most of us don't think like that, I decided to write it in the standard way. Most of you think of it like this. And then you're like, okay, acceleration should be negative. What's velocity 1 initial?
So 20 meters per second.
Nope.
Negative 20 meters
Yep.
per second.
You know what I'm saying? And so if we had flipped it, you would have been right. And so V final is, I don't know. Do we know the distance it traveled? We don't. But we do know, wait, how high above it was it? It was 200?
It doesn't say.
200.
So,
Oh yeah, 200. We know total.
Yeah, so we know it's 200 minus h, right? We know that 200 meters is equal to delta y1 plus delta y2 absolute valued, right?
So that delta y where you wrote 200 minus h, that would be for the second problem. No?
No, so if this distance is h, isn't this distance 200 minus h?
Okay.
Again, this
got
is
it.
200, this is h, this would be 200 minus h. Okay. Luke, we still have about 15 minutes, all right? We're still in lecture, just so you know. All right, so, yeah. All right, so in this case, that's how I got this. And then the time is, I don't know. The time, I don't know it. So now down here on this one, on this stage, I'd say, wait, what is delta y2?
H?
Nope.
Minus h.
Negative h, because you went downwards
Oh my
h, right?
God.
Do you agree flipping the coordinate system would have been a smart idea now?
Yeah.
Yeah, and so this is why if everything in a problem is going down, it's much better to flip your coordinate system because that's 3 different minus signs. The odds of you missing just one of them and screwing up the entire problem is non-trivial. All right, anyways. So And you notice I don't really care about the order of the subscripts here, like one final versus final one. Who cares? What's V2 final? That's 0. It didn't tell us what this number is, did it?
Well, it would be, yeah, because it's G minus the G6.
Oh,
Or
okay.
I should say plus G6.
Okay, so it's going to be G.
Or negative G, right? Negative G plus G6.
Yes. So if there was, yeah, exactly. So how about this? It's G minus G over 6. Now think, if you're moving down and slowing down, shouldn't the acceleration be upwards? Right? Otherwise, now notice, negative velocity, positive acceleration, slowing down to 0. That makes sense. Opposite signs. Now, if you're in free space, this thing says you can accelerate with rate g. Well, now that you're close to the moon is causing you to go downwards at rate g over 6. Then you have g upwards. The net effect is this, 5, 6 g. And I think that's what it says. Yeah, in free space, you get a maximum rate of g. Well, the moon is going to kill off 1/6 of that. So you only get 5/6 upwards. Crazy.
Mr. Joystead?
Yep,
So the change in y and 2 is negative h?
that's right. Because we're
And then
going down distance h. And then, oh, this one right here. Is that what you were
Yeah.
saying, Memo?
Yeah.
Do you agree I screwed up right here? See, even I screwed up. We should have flipped the coordinate system. I think every single person here has made a mistake, except for Memo. Good job. So this would be negative 200 minus h. Whew. Right? Oh my goodness. So, wowza. Let's take a look in the solutions and see what I did there and see if I chose to flip it or not.
So because it says, so when it reaches height h, it turns on its thrusters to maximum, which means that it's applying a force of g.
No,
Right.
G is not a force. What we know is that the force would cause it to accelerate at rate G. But we know that the moon is causing a force that would cause it to accelerate at G over 6 downwards. And so the force from the thrusters up minus the force down, we will cover that more in chapter 5. So this one is really, pushing your limits. This is really stretching. If you get confused on this one, that's fine. Use the solutions. It's definitely more 161 level than it is a 110 level. It's barely doable at your, yeah. All right. That said, what were we looking at? So there it is. Oh, I did flip it. You see that? Yeah. And what does that do for me? Notice it's still not easy because I flipped the coordinate system. So notice this is good practice. All right. So in this particular one, when I flipped the coordinate system, this was positive, positive, positive. And then this one is now going opposite the coordinate system. So that one becomes negative. So no matter what you do, this problem is confusing. And so if you have to get out the solutions and look through it, you can go ahead and do that. Yeah, okay. So it's all there. It's all there. All right. We still have 10 minutes here. I want to check and see. Let me see if I did the plots for this and see if this makes sense. Nope, I didn't. No, that's interesting. 54 meters above. Yeah, so, okay. this is good to note. Once you know one piece of the puzzle, everything else works out. The hardest part in your physics question is getting that first part correct. And so, what are the strategies? The strategies are list your crap and write your equations. Listing, it's so important to get this right. So this is a great problem if you want to redo it. And there's other ways to do it than this one. Then notice, what did I do? I went to my equations and saw which ones are going to work for me. Now, and you could see that here, this gave you the insight as to why I chose to write these equations, the v squareds. And it was because I know the velocities and some heights and the accelerations. I can get the other velocity really quick. Once you do that, you can hopefully do whatever you need to do. So, yeah, that's this part right here. Make sure you read that. And I'm going to pause for a second, see if there's any questions. Whoops, I got a cable caught. That's pretty intense, isn't it? Like I said, we're trying to train harder than the test questions. So if you're freaking out right now, that's fine. Hopefully your test questions will seem easier than this. Hopefully. Yeah.
We're
All right.
also gonna work on XT and VT graphs on the test too, right?
Yep. And so the test is about equally split. I didn't look at the exact points, but so there's a bunch of questions. I made up a whole bunch of XT graph questions, a whole bunch of VT graph questions. I don't think I made any AT graph questions. And so I'm asking you about those graphs. And making you figure out stuff like distance or displacement or velocity or change in velocity or things like that. Moving forwards, moving backwards, all that kind of stuff. And then there's word problems. Some are horizontal, some are vertical. And sometimes I ask like a simple question, like which of these things should be positive or negative? Because you could see, based on what we saw today, it's easy to mix that up. But hopefully you're getting more particular about that, a greater attention to detail for when things should be plus or minus. Because if you can't get the signs of something right, you're never going to get the whole problem right. So, yeah. You want to look at one more graph question really quick just to see how we do there?
Sure.
I thought, yeah, let's look at 232. We haven't done a ton with the A graph, but I think there's something you can learn from this that applies to the other stuff. So let's take a look at it. Let me bring it up. What was I? I was going to look at page 39. All right, there it is. So I'll give you a second to look at that. Okay. So in this case, up till now, we've always been doing this really crazy crap where the acceleration changes in a very jerky manner. And that's good enough to get the job done. But this is starting to be a little bit more realistic. And that usually means more tricky. But this is supposed to be a car starting from rest at a stop sign, and then it accelerates. Just imagine if you were driving a car, right? You start from rest, you're going to step on the gas and start to accelerate quickly. And then when you get close to full speed, you're going to let off the gas and accelerate slowly. So, okay, based off that, let's do part A together. Just take a guess. When will the object have the greatest speed?
At the greatest acceleration?
Nope.
No.
Nope.
At
The
around 2.
Nope.
T equals 8.
At t equals 8. Now think about this. What does this mean? And this is something you can get out of this. Area equals change in velocity. When you're on an AT graph, that's the only thing there is to get out of this. So take a look. This is a positive area. Your velocity increases. This is a positive area. It increases. All of this is positive area. And in fact, if I could, right, you can see if you just draw a triangle there, all of this is basically a positive area. That's going to get you your change in velocity. Well, isn't this area over here also positive? It's also increasing. Another way to say it is this. Right here, your acceleration is small. Your velocity is changing not that much. Here, your velocity is increasing at a larger amount. Now your velocity is starting to increase a lot. At this point, that is the point in time at 4 seconds when your velocity is increasing most rapidly, but it's still increasing. You still have a positive A and a positive V, still have positive A. So here, right over here, your velocity is still going up, but it's not going up that fast. And then right here, you're basically at full speed. You're hardly increasing at all. Does that make sense for part A?
Yes, it's deceiving.
Isn't it? Yeah.
Because
right?
it makes you think if acceleration is going down, then you're slowing down. So that's why I thought,
Yes.
well, at the top of the curve is where your highest velocity is, but it makes sense because it's all adding together. You're not
Exactly.
slowing down, you're just not speeding up as much.
A is greater than 0. It's getting smaller, but V is greater than 0. Whenever that's true, still speeding up. Here, A is greater than 0. V is still greater than 0. And so that trick works pretty well and you can see that it is very difficult to know everything inside and out. And so that was basically, and I think from here you can get the area. I do want to point out, remember that the area is not velocity. The area is delta V, okay? Delta V, change in velocity. All right. That's pretty good on that one. Let's try one more here. Whoops. I saw it here a second ago. This one has been a good one for years. It really gets people, which means hopefully it finds a misconception is what I'm saying. 2.30. This is page 37. Page 37. So we aren't going to do the whole thing here, but well, maybe we'll try to do part A and then call it a day. All right, so we're trying to make a VT plot. Somebody help me out. Whoops. What is this piece of information telling me?
VI, the initial X is -2.00.
I love it. So that tells me that. Is everybody okay with that? Moving. That's the key word that makes you think velocity. Backwards, -2. All right, that's good stuff. Let's get rid of that. Okay. So now, whoops. Let's go to this one. Okay, there's a lot in there. What does that tell us?
It's going to be a constant speed all the way towards till it hits 2, and then
That's
it's
good.
going to change, but I'm not sure how.
Okay, you're right. So that's the key. That's a fancy way of telling us acceleration is 0, right? So, right, this tells us A equals 0 for 2 seconds. That's sneaky. All right. So somebody else, now it's going to accelerate for the next 3 seconds. I do know that. Where is this? So now we know it accelerates uniformly. And at the end of this, blah, 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 blah. Geez, that's a lot of words. What does that mean? Somebody else.
So it's moving opposite direction. So that means it's going to the right, or I guess
Okay.
it's going.
So it's going to be
And then
somewhere
it's-
up here.
Yeah, and then it's going 3 times. What did it say? 3 times the initial speed. So -2 times 3. Well, it would be the speed. So it'd be 2 times 3,
Yeah,
right?
which is,
6.
yep, okay.
So we're going to 6 meters
So
per
at what
second
at what time does it hit 6?
at 3 seconds.
Nope.
For the next 3 seconds. So at 5
Yes.
seconds.
And then what else does that tell us? If it accelerates uniformly, what does that mean?
That's a straight line.
Right? That's a lot. And then somebody else, it says it comes to rest at constant rate in 1 second. All right. So what does that imply?
It goes to 0 in a straight line.
Yep. And so from there, now we're off to the races. And now, so you have to create the plot yourself before answering it. This was a particularly unpopular test question I gave once in 161. Because everybody couldn't get part A because they didn't read carefully enough. And that's when I realized, I need to stick this in the book so they could practice this. So there's some good stuff in there. And let's call that class for today. You could do the rest of that one at home. But you could see that there's a lot to reading these words carefully. It's really just a lot of this class is just forcing you to make dumb mistakes so that you learn to be a better reader and better note taker and more organized and things like that. That's it.